We had a question about Math 3A at UCLA. Here's our video response.
Guys, here's some questions that I didn't get a chance to finish or answer during the last review. So this is back to the 3A review. Remember that question we were working on? And it did that box problem that one of the students brought up? And I thought about it, I was like, this is way too hard, they wouldn't be doing this. And so actually what the student said, I think I misunderstood him. He said that it was a box, and I thought he was saying the whole thing was a cube, but then there'd be nothing to do. So what the professor meant by that the bottom was a square. So that actually made the problem much easier. So it turns out that the bottom was given to you as a square, and then if you run it that way, it is much, much easier, and it fits very well along the lines of the problems we were looking at. Okay, so let's finish that problem. In fact, since it's not that bad, let me just run it from the top. Okay, so I think we had something like this. This was my original picture, but that problem, which could be doable, actually we need a little more information to finish it. It was already looking pretty tough, right? The original version that was posed, you have this box, right? The top was open, so there's no material. You surround this whole thing with material. And I think it was something like the bottom was $2, I think, per square meter or square foot or whatever. And then the sides, all three, 1, 2, 3, 4 sides, was something like $5 per square meter. Okay, that was the rate. And then the one big thing that makes the problem a lot easier that the student pointed out that apparently I didn't pick up on was, if I read the problem carefully, I would have noticed this bottom here, it's not a rectangle, it's a square. Okay? So that makes the problem way easier. In fact, since it's a square, these two sides are the same, right? So if these two sides are the same, and then all we have left is the length up here. I mean, we can make width, length, height, whatever, right? We'll run the same computation again to see how much easier this is. So remember, here's the cost. So again, the idea is, I want to make a box, the top is open, right? The bottom, to make the bottom requires $2 per square foot. To make the sides, this back side here, this side, and this side in front, the front face, those 4 sides cost $5 per square foot. Okay? And I gave this side, because it's supposed to be square even though it doesn't look like one. And the height or the length up here. Okay. So first we had the volume. The volume has got to be, so L times S, which in this case would be LS squared. Right? Okay, nothing going on there. The second thing was, what are we trying to minimize, right? In this problem, the question was, minimize the cost. So what shape would you take to minimize the cost? Okay? And there was a fixed volume given, and I think the volume was given to you at 100, cubic meters. Okay. So the idea was minimize the cost. So L times S is the volume, so LS squared, right? Then I want to actually compute the cost. So I have this fixed information. Let's compute the thing we're trying to minimize, the cost. So the cost would be, well, you need to pay for the base, and the base is just S squared, right? Because that's the area of the base. So the area of this guy here, this area is S squared, right? And then that's in square meters, right? How much is it per square meter? It's $2. So I guess it would be 2 times that. Okay, no big deal. Then I have to take out the other sides. So if I look at the other sides are S times L. So the area of this side, for example, is S times L. And if you look carefully, it's also S times L for this face, S times L for the back face, and S times L for this face. So all together we have S times L, right? The cost is $5 per square foot, or square meters, sorry. So each one of these, so total number of square meters times 5 to give you the $5 per square meter. And then on top of that though, it's not just one side, like we just pointed out, there are 4 sides. So it would be 4 times this amount. You sum all that together, you get the cost. So the cost is actually going to be 2S squared plus 20SL. Okay, no big deal. And you can see this is much easier than what we looked at during the midterm review. All I need to do is do a substitution because I don't want to have 2 variables. So let's do that really quickly. Since 100, the volume is LS squared, we need to substitute for someone. I think I'll do, why not L? Why not? So we'll say L happens to be 100 over S squared, right? Let's come back and plug that in. So now the total cost is 2S squared plus 20S times what used to be L, still L, but substituting 100 S squared, right? Nothing big going on here. The S's would cancel out, and I end up getting something like it's 2S squared plus 20, well I guess times 100, over S. Okay, so Not too bad, right? Okay. So now we have this function, and this was actually our cost function, right? What we want to do is minimize. Technically what we should be doing though is we should also be checking the endpoints. But the endpoints are, what could these minimal values be? Well, the smallest length that you can have is s. But the smallest length you can have for any side is 0. But if L were 0 or S were 0, the volume would be 0, so that doesn't make any sense, right? So I'd have 0 as one endpoint, like we just said. The other endpoint technically would be infinity. Because if you have to multiply to give yourself 100, and one of these guys got super, super big, the other guy would just have to get super small to compensate, and you might still be able to get 100. So there's really no endpoint out there. Okay, so just being technical, 0 doesn't work for us, infinity is not an endpoint, it just keeps going forever, so we don't have to worry about that. Okay. Now I want to check the critical points. Remember how to do that, right? To get the critical points like usual, take the derivative. Okay? So nothing complicated here. We're not going to have to do the chain rule because we're taking the derivative with respect to s. So this guy's really easy. This is 4s. How about this thing? I'll clean that up. So that looks like let me see this. So 2,000 up top, and then I'll rewrite this. So let me rewrite this really quickly. This guy is the same as 2,000, right? Just multiplying this out, s to the negative 1. So let's take this derivative. So it would be negative 2,000 s to the negative 2. Okay? Nothing big going on here. So this is my cost function I like to minimize. Okay. So let me take this away. And we'll clean this up. You know what to do, right? To find that max or min, set it equal to 0. So 0 is equal to 4s minus 2,000, and we'll write it like this, over s squared. Same thing, I just want to write it in a convenient way. Okay? And then if I wanted to, I can add to both sides. So 2,000 over s squared is equal to 4s, right? Multiply both sides by s squared, right? Again, divide by 4 just to clean it up. So 500 is s cubed. Okay. So then I guess s would have to be the cube root of 500. Okay, not super pretty, but good enough. Okay. Then to finish this, well, first I've only got one critical point, so this will probably be the winner. I need s, but maybe he wanted the dimensions of the entire box. So you know it's cube root of 500 by cube root of 500, s and s, right? By L. But what do you know about that? Go back to your original linking formula. The volume, which was 100, was s squared L. So if we plug this in, so the cube root of 500 squared times your length is equal to 100. Just substituting in. So you could solve for L. Again, it doesn't look pretty, but if you cranked it to a calculator, it would not be bad at all. It's 100 over the cube root of 500 squared. Okay. So not too bad. Again, if the professor's being really anal, he might want to say, how do you know? You found your critical point. So this is the only one that's going to work for us. It's either a max or a min. How do you know for sure it's a min? Well, one, in order for this problem to work, it should be a min, right? But two, if we want to check, you can check it either way. We can do first derivative test or second. Since during the review we focus on the first derivative test, well, let's just do an application of the second derivative test. So we have the cost function's derivative with something like, I think, 4s minus, what was it, 2,000 over s squared, right? That was our derivative. Okay, so let's do the second derivative test, just for practice. So c double prime is 4, right? Derivative 4s is 4. And I compute this, I think in my head, take the derivative, that's positive 4,000, negative 2 times 2,000, s to the negative 3. And then we get, what is this? So for our final answer, plus 4,000 over s cubed. Okay, something like this. And really don't have to do a lot of work. Technically take our point, but we don't have to even finish this. S is a positive number. Then this is positive over positive plus another positive number. So I know c plus, or double prime, sorry, is positive. And remember it's the opposite. Positive means you're concave up, so that means your relative min. So I think we're good. Okay. I'm going to do a couple more problems really quickly. So we're going to shift gears. I might have to actually split this up into different videos. But now we're going to actually look at some of the graphing problems I wanted to get to but couldn't on intermediate value theorem.
Like John says, no stress.